Cool. Hey everyone, my name's Wang, and I'm excited to talk today on our work on influencing towards stable multi-agent interactions to help tackle some of the difficulties of learning in non-stationary multi-agent environments. So coordination is often critical to succeeding in multi-agent environments. For example, in this household, there are two robots, a blue and a red one, that have been given the task of cleaning the entire house and the front yard after a long night out at a dinner party. So the two robots can take on many different strategies when deciding how to optimally clean this house. So let's say that we are the blue robot and we need to decide which trash bag to pick up next. So when deciding which trash bag to pick up, we really have to decide based on what we think the red robot will do, as we don't want to have to clean up the same trash bag as the red robot is to avoid being inefficient. So partners with changing strategies make learning in multi-agent environments really difficult. So without knowing what the red robot will clean, the blue robot may accidentally interfere with the red robot and pick up the same trash bag. This leads to a coordination failure since each robot's redundantly picking up the same trash. So the key problem here is that non-stationarity in the other agent's strategy makes learning really difficult. Without knowing what the other agent might do, it's difficult for the ego agent, the blue agent, to behave optimally. So prior works in opponent modeling suggest both reactive and proactive approaches to dealing with non-stationarity in these multi-agent environments. A reactive algorithm for the ego agent could be one that tries to forget past experiences, or maybe just retrain on more recent data, or even predict the opponent's strategy with some learned model of the opponent's behavior. So in terms of the robot cleaning example, a reactive algorithm for the blue agent might greedily move towards the nearest trash bag, or as the red robot moves towards one trash bag, the blue robot could predict where the red robot's going and move towards the other trash bag. However, predicting the opponent's strategy can be done in a proactive way as well. A proactive approach might try to learn a dynamics model of the opponent's strategy, or even use this dynamics model to influence the opponent towards some desirable strategy. And in this way, the robot is learning how to proactively influence the opponent's behavior rather than just react to the opponent's behavior. And in terms of the robot cleaning example, now the blue robot might proactively predict that the red robot's going to move towards the bottom trash bag, and then know to move towards the top trash bag. So in principle, it'd be great if the blue robot could always precisely predict exactly where the red robot's going, but this isn't always possible, especially when there's many, many trash bags. So, but if the blue robot could stabilize the red robot's strategy, then this could make learning a best response much easier. So in the context of cleaning the house, the blue robot could wait for the red robot to go outside, and then this might seem a bit silly, but the blue robot can then go, close, lock this door, and then which will stabilize the opponent's strategy to only clean the trash on the outside in the front yard. This effectively will partition the cleaning regions into two, so making each robot's role in cleaning the house much more clear. And this simplifies the entire learning process and will help them clean all the trash. So our key insight here is that stabilizing the other agent's strategy in a multi-agent environment can reduce non-stationarity and facilitate learning a best response to the other agent. So for our problem statement, we consider two-player multi-agent settings where there is an ego agent that we have control over and another agent that we don't have any control over, don't have direct control over. And as a specific example to introduce this problem, let's take a look at this circle environment where the ego agent is the blue circle, and the other agent chooses a goal location between any of these three gray goals. And the other agent's hidden strategy, shown in red, is this choice of goal, denoted by Z, and the ego agent doesn't observe the opponent's hidden strategy. The ego agent's task is to try to get as close as possible to the opponent's chosen goal. So we consider the setting where the ego agent's, where the opponent's goal location transitions based on the ego agent's trajectory. So in the circle environment, if the ego agent ends its interaction inside of the circle, the opponent will move its goal location clockwise. Otherwise, if the ego agent ends its trajectory outside the circle, then the opponent's goal location will stay stationary. And since the opponent's goal location is unobserved, stabilizing to one unobserved opponent goal will make it much more easy for the ego agent to learn how to navigate to that unknown goal. So with this problem statement, our method seeks to stabilize the opponent's strategy to help learn in a multi-agent environment. So as a definition, we define two opponent strategies as pairwise epsilon stable if the distance between those two strategies is less than epsilon. So if we go back to our circle environment, we can now look at what stabilizing the opponent strategy would look like here. So if the blue agent ends its interaction inside the circle, then the opponent will move clockwise, and the latent strategy would be some distance away. And we want to minimize this distance between consecutive interactions in order to stabilize our opponent's strategy. So stabilizing behavior here would be for the ego agent to continually end its interaction outside of the circle so that the opponent's goal location will stay stationary. So we can now present our method, stable influencing of latent intent, or SILI, which is composed of two main components. And the first is a representation learning component, and the second is stable influencing via reinforcement learning. So I'll first describe the representation learning component on the left, which is how we learn a model of the opponent's latent strategies. So we can approximate the latent strategy dynamics by learning an encoder which maps the previous trajectory to the predicted next latent strategy. And in terms of the circle environment, the ego agent's trajectory is fed as input, and the output of the encoder is the next predicted latent strategy. And since we don't observe these latent strategies directly, we can't learn these in a supervised manner, but we can learn them in a sort of unsupervised way, since we know these latent strategies should be predictive of the task rewards and the transitions, which we do observe. So we can train this decoder that predicts the task rewards and transitions from the encoded latent strategy embeddings. And again, in terms of the circle environment, the ego agent's last predicted latent strategy, as well as state and action, is fed as input. And the output of the decoder is the predicted task reward and the predicted next state. So with these learned latent strategies and the dynamics model, we can now stably influence with reinforcement learning on the right-hand side of the diagram. So with these learned encoders, we can define a stability reward using the distance between consecutive opponent strategies. Then we can define a new reward, our total, as a linear combination between the task reward and the stability reward, parameterized by a stability weight of beta. And with beta equals 1, the SILI's entire objective is to stabilize. And with beta equals 0, the ego agent will just greedily maximize the task reward. And we can now train our policy using our total. And since our stability objective is to keep the opponent's consecutive strategies stable, it's important to condition our ego agent's policy on the last two predicted latent strategies. So in the circle environment, SILI can optimize for R stable to always learn to end the interaction outside of the circle to keep the red goal stationary. And once the opponent strategy is stable, the ego agent can begin to creep towards the true goal that's being kept stable, which is why we optimize for our total. And finally, we train our encoder and policy simultaneously. So as the encoder's representation for the opponent's strategy improves, the ego agent's policy can adjust in the loop as well. So we examine three methods for modeling and measuring distances between latent strategies. The first is continuous latent variables. The second is discrete latent variables. And the third is where we have partial observations of the changing strategies. So in the most general case with continuous latent variables, we allow the latent variable space to be unconstrained and use the Euclidean norm for the stability reward. And these continuous latent variables would make sense to use, for example, in the circle environment when the goals can lie anywhere on the continuous spectrum along the circumference of the circle. In the discrete latent variable setting, we use the Gumbel softmax distribution to constrain the latent variables to be categorical variables. And with the categorical latent variables, we use the discrete distance metric for the stability reward. So intuitively, it's easier to identify whether or not two strategies are similar enough to be clustered together than it is to identify the exact distance in this latent space between the predicted latent strategies. And finally, we have, so when we have prior knowledge that there might be a discrete number of opponent strategies, it might make sense to use discrete latent variables. And then finally, we have this setting where we have partial observations of the changing strategy, where we assume the ego agent can observe if the opponent strategy changes between time steps. So no representations learning is required in this setting to stabilize. And this corresponds to a setting where, again, it might be easy to identify whether or not opponent strategy might change between time steps, but really difficult to estimate exactly what their strategy is. So for experiments, we run experiments in a variety of simulated environments, including multiple variants of this circle environment, a driving environment, an assistive robot reaching environment, and an emergent communication environment. And for the sake of time in this talk, I'll present results in the circle point mass environment, specifically the variant with 3 goals, but we have much more results on our website and in our paper. So as a reminder, in this environment, the ego agent is in blue, and the opponent chooses a goal location in red. And the ego agent must try to get as close as possible to the opponent's chosen goal location in red. And for the strategy dynamics, if the ego agent ends its interaction inside of the circle, again, the opponent will move clockwise. Otherwise, the opponent will stay stationary. So for quantitative results, we compare our approach with multiple baselines, which I'll now introduce. So we show the task reward on the left and the stability reward on the right. So our first baseline is soft actor critic, which is the baseline reinforcement learning algorithm of our method. We use vanilla soft actor critic as a comparison for an algorithm that doesn't have any explicit opponent modeling. Stable is a variant of silly with the beta set to be 1. So stable is only optimizing for stability of the opponent goal, as can be seen by the really low task reward, but the very high stability reward here. Surprise minimizing RL or SMRL optimizes for a different notion of stability, where the surprise reward is proportional to the likelihood of the state given the history of the previous states. But notice here that SMRL doesn't optimize well for our stability objective. Lily, learning and influencing with latent intent, combines soft actor critic with representation learning to model the opponent's strategy dynamics as well. But unlike our work, Lily doesn't optimize for stabilizing the opponent's strategy at all, as can be seen by the low stability reward here. In our method, stable influencing of latent intent, or silly, achieves the highest reward here by learning to first stabilize the opponent's strategy and then maximizes the task reward with respect to that fixed strategy. And finally, we have an oracle as a baseline, which is given the true opponent strategy as an observation. So notice here that silly and oracle achieve similarly high rewards, but that the oracle doesn't need to stabilize the opponent strategy at all in order to maximize the task reward. So for some qualitative results here, the first we have here is soft actor critic. And so recall that soft actor critic does not model the opponent strategy at all. And so the local optimum is to move towards the centroid of the 3 goals when the true goal is unknown. Lily does learn a latent representation of the opponent strategy, but doesn't optimize for stabilizing. So as Lily greedily optimizes for the task reward, Lily will creep towards the boundary of the circle and could encounter an unexpected transition of the opponent strategy. Stable is that variant of silly that purely optimizes for stabilizing. And notice here that stable does learn to end every interaction outside of the circle, which stabilizes the opponent goal, but stable has no incentive to move towards the opponent's true goal. And finally, silly, our method, learns to stabilize the opponent's strategy by safely ending each interaction outside of the circle. And by doing so, silly can more easily optimize for the task reward by going near the red target. And to summarize our key contributions and takeaways, so we propose learning an unsupervised stability reward to influence other agents towards stable strategies. And we show that silly improves our robot's ability to coordinate and maximize the task reward. So thanks for listening. And here's a QR code that links to our project's website. I'm happy to take any questions now.
Questions from the audience? So one, I'll ask quickly, Woody, great talk. What about, have you thought about how robust it would be to noise? Have you done experiments injecting noise into these environments?
So let's see, with respect to noise. So I guess one of the things we're really interested in is looking at, I guess, more complex environments with more opponent strategies, and specifically, I guess, the noise of the real world too. Like a lot of the COVID restrictions. I've been in Texas this whole time while working with Dorsa from Stanford, and so I unfortunately haven't been able to do some real robot experiments yet. But we've been really interested in thinking about, for example, this steak cutting example, where if we have like a bimanual robot that's trying to cut a steak, so if we think of the 2 arms as each agent, then I guess if our objective is to cut the steak, you could imagine stabilizing could be like one of the arms could perform stabilizing behavior by holding a fork and like stabbing the steak and holding it still. And then the knife, so that's essentially is going to stabilize the opponent's strategy if you think of the opponent as the steak's dynamics of moving. And then the knife can more easily cut through the steak. And so I guess with regards to noise, we'd be really interested in looking, I guess testing this in the real world.
Okay, good. Yeah, other questions? Here's one from the back.
What are the dynamics like for having two stabilizing agents in an environment?
So if you have two agents trying to stabilize each other's strategies.
Yeah.
So this is, I guess this is leading to a really good point of like, when is it possible to stabilize an opponent's strategy? Or and so I guess the way we've thought of this problem is that it's kind of like so Lily tries to influence the opponent's strategy in the sense that just to maximize the task reward. But we were really interested in looking at like how can we like explicitly influence? And so we can think of stability as just an inductive bias of saying like when our opponent's strategy might be changing a lot, if we can keep it fixed, then we can at least learn the best response to that fixed strategy. So if two agents are trying to stabilize each other, I guess it can be, I guess it depends on the environment on whether that's actually possible. But so one thing we've also looked at is making sure that this method doesn't hurt in environments where it's not possible to stabilize. So we do provide experiments on annealing the stability weight. So where you might want to start out trying to stabilize your opponent, and if it's kind of not possible, then you asymptotically will then just optimize for your task reward as you would have done so initially.
Thanks.
Great, thank you, Woody. Okay, so I don't know, Jans, if there's anyone online with a question. Otherwise, you'll introduce the last speaker of the session.
No, we didn't get any online questions. So if there's still any questions, you can also ask them during the poster session.